Hi guys, welcome. Today is day 30. We're looking at lessons 77 and 78. Let's go ahead and flip over to 77. We're looking at today inequalities with negative coefficients. So an inequality greater than, less than, greater than or equal to, less than or equal to. So we have two inequalities. Okay, we've studied this probably since elementary school. Again, the opening is going to the larger side. So A in this case is greater than B because, again, if we wanted to draw teeth on there and think of it as an alligator or whatever, it's eating the larger number. So A is greater than B. If A is greater than B, then A plus C is greater than B plus C. So if we add the same amount to both sides, well, if A was greater than B and we add whatever C is to both sides, then A plus C is greater than B plus C. And if we take the same amount away, well, A minus C is still greater than B minus C. A times C is still greater than B times C. A divided by C is still greater than B divided by C if C is not equal to 0, in which case they would be equal because it's infinite or undefined. We can't divide by 0. So that, again, 0 is kind of always our rule breaker. We can't divide by C. And then if A times C, if C is negative, then it's the opposite. Then because AC or A times C becomes less than B times C if C is negative, because it's going to be further from the origin. It's going to be, like if it's positive 30 and positive 20, 30 is greater than 20, but then make it negative. Negative 30 is less than negative 20. So in the past, we've showed you how to solve these multi-step problems with equal signs or inequalities. We treat it just like an equal sign, and if we do something to the left, we have to do it to the right and just work until we get our unknown isolated. It's going to be the same procedure, except there's one extra step that we have sometimes. If we are incorporating negative numbers, then that's going to affect what we do, whether we're multiplying or dividing. And we'll take a look. Again, if we look at the opposite, 6 is greater than 5, well, negative 6 is less than negative 5. Then if we have one of these problems, let me copy, no. So negative 3. It's greater than 8. All right, so again, we're not going to write in an equal sign, but we've done since 5th and 6th grade, we've isolated these variables. We want to get x by itself, either on the left or the right side of this sign in this case. So we just think inverse operations like we've done in the past. So don't worry about this right now. There will be one extra step we have to do, but we'll worry about that when we get there. So first thing we do, we have minus 10. So we have to add 10. If I do it to the left, I have to do it to the right. Negative 10 plus 10 is just 0. I still have my negative 3x, and it's still greater than 10 plus 8, which is 18. Now I'm going to divide, but I'm going to be dividing by a negative 3, because negative 3 divided by negative 3, any number over itself, same thing with negative numbers, is just 1. So I don't want to know what negative x is. I want to know what x is. So I divide negative 3 by negative 3. Have to do the same thing over here, and I get negative 3 over negative 3, just gives me x, and then 18 divided by negative 3. But since I'm dividing by a negative number and I'm flipping the signs of both sides, that means I have to flip the inequality. And then 18 divided by negative 3 is negative 6. So any value less than negative 6 would solve this inequality. And let's take a look, because here was our original. And let's say we didn't flip the sign. Well, let's just check it. We did flip the sign, so this is correct. So I don't want to confuse you too much. This is correct. So let's pick a number less than negative 6. Let's do negative 10. Negative 10 should satisfy this inequality because it is less than negative 6. So if I put in negative 10 in for x, Okay, well, -3 times -10 is positive 30. Positive 30 minus 10 is 20. 20 is greater than 8. So that's why I flipped the sign, because if I hadn't, we would end up with an inequality that said 20 is less than 8, which obviously is not true. So that's why we had to flip the sign, because we're just like the first example. 5 and 6. 6 is greater than 5, but -6 is less than 5. So when we're changing the signs of both sides by multiplying by a negative number or dividing by a negative number, we have to flip this inequality. You could think of it when we do it with an equal sign, but flipping an equal sign is just still an equal sign. So that's why we never really talk about it when it's just an equal sign. But when it's an inequality, we have to do that step, or else it's going to be incorrect. We did it correctly because we changed this when we divided. We ended up with a negative 6 because we divided both sides by a -3, changing the signs of both sides. So that's why we flipped this. It was opening to the left. Now it's opening to the right. And then we plugged it back in just to check to make sure that it was correct. When we have an equal sign, we're looking for one number that satisfies the equation. When it's an inequality, we're looking for a range of numbers that satisfy it. So that's just one extra step that we may have to do. So just be aware, if you're multiplying or dividing by a negative coefficient, you're going to have that one extra step. Let's see if we have any that are arranged. No, we don't have any that are within. Is that the one we just did? Nope, 3. Let's look at 4. We have a word problem. This one, again, we want to get rid of parentheses because we can't combine x and -3, x and -3. So we just distribute. We get -5x plus 15 because -5 times -3 is positive 15 is greater than 5x minus 15. And we want to get both of our x values on one side. What I would do is I would add 5x over, just because we know that that's going to give us positive 10x and a positive coefficient. So then we wouldn't have to change the sign. But we can do it the other way, minus 5x from both sides. We get -10x plus 15 minus 15. From both sides, we get -30. Divide by -10 and flip the sign at the end. And then again, like always, it's a test or something important. Plug a number in back to your equation and see if it works out to be true. So let's look at example 4. Marcy sees a shirt she likes that costs $50. She will not buy it unless it's $30 or less. To find the percent decrease in the price required, she solves the inequality. 50 minus 50x is less than or equal to 50. Oops. Make sure I input it correctly. Okay. Now this line below, I know we've talked about, but this means less than or equal to. So we can have a number that's equal to a value or less than or equal to. So that just, in those examples, we use shaded circle on our number line to indicate that that number will satisfy. If it's open, it means this number will not satisfy. All right, so from here, what we want to do, we have a positive 50. We want to get rid of that, so we subtract 50. 50 minus 50 is just 0. And we got to subtract 50 over here. 30 minus 50, -20. And then we still have this negative sign, so don't just because we got rid of 50, this still is here, so we got to account for that. We can't just get rid of it. And then I divide both sides by -50. I'm dividing by -50, so this symbol has to now flip this way. Don't get rid of the or equal to, but now it's just saying greater than or equal to instead of less than or equal to. -50 divided by -50 is just 1, so 1x, that's good. We want to know what x is, not -x. And then what, this 10 goes into it, and then -2 over 5 is both of those positive, so x is greater than or equal to 2/5, which, let me look back at the original problem. I think we were looking for a percentage, so 2/5 multiply 2 divided by 5 gives us 0.4 or 40%, or we could do 20 over 50 both of those times 2 to give us 40 over 100 or 40%. So percentage-wise, fraction was 2/5, so the percent is 40%. All right, so that's 77. 78, we're looking at products of square roots. So again, square roots, the square root of 16, the square root of 81, the square root of 100. We have perfect squares that work out to be a whole number. And then we have like the square root of 2 or the square root of 3, which is an irrational number because it's a decimal number that continues on forever. So we can round it, or we can write it as root 2 or root 3. Okay. The property we already talked about before, but a good reminder, if we have the square root of a times b, we can break that apart to the square root of a times the square root of b. So if we have, I know this is one of the common ones that we use with our 3, 4, 5 right triangles and the Pythagorean theorem, but if I have what's an example we can think of? Okay, if I have square root of 50, I can call that the square root of 25 times the square root of 2. Well, why does that help me? Well, the square root of 50 is irrational, but there's a perfect square that's a factor of 50, which is 25. So I can take out square root of 25 times the square root of 2, same thing, and then I get 25, square root of 25, times the square root of 2. Well, the square root of 25 is 5. Square root of 2 is irrational, so we would just leave it like that. So we'll see some of these test questions. Don't just hit square root of 50 in your calculator and then give me a decimal number. You're going to get that wrong. So we want to think about this in terms of this rule of a times b under a square root sign means we can break it apart into the square root of a times the square root of b. Or opposite, if we have square root of a times the square root of b, we can multiply those together and put them under the same sign. So if I had the square root of 2 times the square root of 2, I can then multiply those under square root symbol. Square root of 2 times 2 is square root of 4, which is 2. Sorry, running out of room. So we can apply it both ways. Sometimes it makes sense to break it apart and factor out, and other times apply them together and work that way. So again, we usually write it like this, but we can go from the square root of a times the square root of b times the square root of ab. Find the length and width of this rectangle. All right, so how we can find this, well, we want to find the distance from here to here. There is a distance formula on a coordinate plane, but really all it is just applying the Pythagorean theorem to this. So I can find the distance from here to here and make this look like a right triangle, okay, and then do a squared plus b squared to find out what c squared is. So let's go ahead and draw this out on my own coordinate plane so I can show you. Give me a second. And we had the points -3. 1. -1, -1. Let's see. -1, -1. 0, 4. And 2, 2. Okay. Drawn great, but we can see what we're working with. We have our rectangle here, so we want to find this distance. Now in the past it's been drawn vertically and horizontally, so we can just count the space. We can't just say, well, that's maybe 1 and 2, and this is maybe 1, 2, 3. We can't do that because it's not going horizontal. So we can't just count our boxes, unfortunately. But what we can do is, as I was saying, we can apply the Pythagorean theorem, and I can count over 1, 2, 3, and then down or up 1, 2, 3. And then I can make this little right triangle right here to try and find this distance. So a squared plus b squared equals c squared, what I'm trying to find right there. So this is 9 plus 9, which is 18. Square root of 18, well, that's going to give me an irrational number, but I can break it apart to square root of 9 times 2. Okay, square root of 9 is 3 times the square root of 2. So I can call C 3 root 2. And so that's this distance from here to here. Again, we said, well, it looks like it's 1, 2, 3-ish. This is going to be a little more than 3, but we can't just count the squares. So that's where we got to use the Pythagorean theorem, try and find these distances in order to find this distance that's at an angle. So we can do that at any point in the coordinate plane. We can do the same thing. To find this would be 1, 2, and over 2. So 2, 2, then would be a right angle right there. So trying to find this distance right here, we'll do 2 squared plus 2 squared, a squared plus b squared equals c squared, which is 4 plus 4, which is 8. Take the square root, well, c equals, again, we can call this square root of 4 times the square root of 2 because we can factor out a perfect square, so let's do that. Square root of 4 is 2 root 2. So this distance right here is 2 root 2. Now, as I said earlier, let's see if we can get this show on the screen. If we want to check our work again, so again, if we want to find the area, we would do 3 root 2 times 2 root 2, which would give us 3 times 2, which is 6. 2 times 2, the square root of 2 times 2 is the square root of 4, which is 2. 6 times 2 is 12. So we can multiply these numbers together as well. Okay? And we can use our calculators to help us out. We do if we do square root, we just do second and then this x squared button that gives us the square root. So if we had, what was it, the square root of 18 out of there, make sure you get out of there. If you're done putting stuff under the radical sign, then make sure you just hit the right arrow to get out of there. Obviously, it's going to affect your answer. We had 18 times square root of 8. So 18 times the second square root of 8. Get out of there and hit enter, and it gives us 12. So that's what's nice, as I said on the example that I said don't put it in. Oh yeah, we did something like square root of 50. So the square root of 50, I said, if you see this on a test, don't put it as just second square root 50, hit enter, there's my answer. No, that's actually an irrational number that continues on forever. So you don't want to put that on the test. We said we could break it into the square root of 25 times the square root of 2, which is 5 times the square root of 2. Now you can use that to check your work to make sure you did it correctly. So this is the example we did earlier. Those are the exact same decimal numbers, so I know that we did it correctly. Or the square root of 25 times square root of 2. Okay, it's all the same thing. So that's something, even though we can't just on a test square root of 50 put that in and put this number on the test and call it good, we can use a calculator to check our work. Well, this is the answer I ended up with. How do I know that's right? Well, you can at least put it in your calculator. Okay, it worked out to be the exact same of where I started, so we know we did it correctly. So that's what I meant by you can't just punch it into your calculator and be done, because we want to leave it in root form if we have to. If it is a perfect square, then we'll just do that. All right, and then these, again, same thing if we're looking at the area of different shapes. This outer one is nice because we D to A here, we can just count over 1, 2, 3, 4, 5. So when they're directly horizontal or vertical, that makes it much easier because we can just count across. We don't have to use some distance formula because we can just count right or left or up or down. But then on this one, we'd have to do the same thing we just did on the previous one. There's 1, 2, 3 as a leg, and then 1, 2. 2 squared plus 3 squared. Take the square root of it, and now it tells us this distance right there. Looks like both of them are going to be squares. So at least if we find one side, we can confidently say we know all 4 sides. And then we'll see some questions like this where we have these. Again, don't just put it into your calculator. You can use the calculator to help us check, but some of them aren't going to work out to be perfect squares. So if I have square root of 3 times the square root of 12, well, again, we can apply that principle and then write them both under. 3 times 12 is 36. The square root of 36 is 6. So in this example, both of these are irrational, but why do we want to work to get them both under the same radical sign? Well, because we end up with a perfect square. Square root of 36 is 6. So that's where it's nice and helps us out. Well, let's look at see if we have 3 root 6 times square root of 15. It will, we don't have a perfect square that goes into 6 as far as a factor. Same thing with 15. But what we can do here, I can break this apart into square root of 3 times the square root of 2. I can do this by the square root of 3 and square root of 2. And since I'm multiplying all of these together, I can, again, multiplication rule, I can move around. It turns out to be the same. So I can say square root of 3 times the square root of 3, and then the square root of 2, or sorry, this was not 2, that's a 5. So 3 times 5. So you got in a hurry and you got to check it. 6 is 3 times 3. 15 is 3 times 5. So we can take the square root of 3 times the square root of 3. We can't do, we could make that the square root of 10 if we wanted. So square root of 3 times the square root of 3, get those under the same sign. 3 times 3 is 9, square root of 9 is 3. So I have 3 times now 3 times square root of 2 times square root of 5. Square root of 2 times the square root of 5 gives me square root of 10. 3 times 3 is 9. 9 root 10. Don't have any perfect squares that go into 10. So again, we're not just doing whatever this would be, or obviously this would be the same thing, not just punching into a calculator, hitting enter, and getting a decimal number. Sometimes it works out to be a whole number. So like for A, with the square root of 3 times the square root of 12, that was the square root of 36, which was 6. So if you put that directly into your calculator and got a whole number, yeah, that works out to be the answer that we're looking for. But for C, obviously, we want to keep it in root form. Since this is irrational and we can't take the decimals out forever, we're going to just write it as square root of 10, or in this case, 9 times the square root of 10. That practice set we will go over together, and then we'll get lesson 79 the next time. Thanks.